Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Michel Rolle, a name perhaps less universally recognized than those of Newton or Leibniz, occupies a fascinating and pivotal position in the history of mathematics. His journey, commencing with a deep engagement in algebra and culminating in a significant contribution to calculus, provides a compelling lens through which to examine the evolution of mathematical thought in the late 17th and early 18th centuries. Rolle's early work, particularly his Traité d'algebra reveals a mathematician grappling with the challenges of equation solving, particularly those pertaining to Diophantine equations, while simultaneously harboring a distinct skepticism toward the burgeoning field of calculus. This initial reluctance, born from a commitment to rigor and geometric intuition, would eventually shape his critical perspective and lead to his most enduring contribution. Rolle's Traité d'algebra published in 1680, stands as a testament to his early dedication to algebraic methods. In this work, Rolle sought to systematize and extend existing techniques for solving algebraic equations. A central focus was the determination of integer solutions for indeterminate equations, a class of problems that traces its lineage back to Diophantine of Alexandria, whose arithmetic served as a foundational text. Diophantines' influence on Rolle is evident in the types of problems he considered and the emphasis on finding rational or integer solutions, as opposed to general solutions encompassing real or complex numbers. Rolle's approach involved a combination of classical algebraic manipulations and innovative techniques designed to reduce the complexity of equations and isolate potential solutions. Consider, for instance, the type of problem Rolle might have addressed in the Traité an indeterminate equation, such as a squared plus b squared equals c squared, possesses infinitely many solutions in real numbers. However, the challenge lies in finding integer solutions, also known as Pythagorean triples. Rolle, drawing upon the work of Diophantine and earlier algebraists, would have employed methods involving parameterization and substitution to generate families of integer solutions. Specifically, one approach involves expressing a and b in terms of two integer parameters, m and n, such that r equals m squared minus n squared, b equals 2 times n, and c equals m squared plus n squared. By varying m and n, one can generate an infinite number of Pythagorean triples. Rolle's work provided a systematic framework for tackling such problems, offering a range of algebraic tools and strategies for finding integer solutions to various types of indeterminate equations. The Traité d'algebra was initially well received, establishing Rolle as a skilled algebraist within the Parisian mathematical community. His contemporaries recognized his mastery of algebraic techniques and his ability to solve challenging problems. The book served as a valuable resource for students and researchers alike, contributing to the dissemination of algebraic knowledge and the advancement of equation-solving methods. However, it is crucial to understand that, at this stage of his career, Rolle remained unconvinced of the merits of calculus. He viewed the reliance on infinitesimals and the lack of rigorous geometric foundations as significant shortcomings. This skepticism, rooted in his algebraic background and his preference for the clarity and precision of classical geometry, would profoundly shape his later engagement with calculus. Rolle's initial aversion to calculus stemmed from a deep-seated concern regarding its logical consistency. He found the concept of infinitesimals, quantities smaller than any decimal magnitude, yet not zero, to be inherently paradoxical. This perceived lack of rigor troubled him, particularly in comparison to the established principles of Euclidean geometry, which he considered to be a model of mathematical certainty. Rolle's algebraic training further reinforced this skepticism. Algebra, with its emphasis on symbolic manipulation and equation solving, provided a different perspective on mathematical problems than the geometric and infinitesimal methods employed in calculus. He sought a more solid foundation for calculus, one that could be grounded in the same principles of logical deduction and geometric intuition that had guided his algebraic work. Figures such as Euclid and Archimedes exerted a substantial influence on Rolle's mathematical outlook. Euclid's elements with its axiomatic structure and rigorous proofs, represented the epitome of mathematical reasoning. Archimedes' method of exhaustion, a technique for approximating areas and volumes by successively finer approximations, offered a geometric approach to problems that would later be addressed by calculus. Rolle admired the precision and clarity of these classical methods and sought to emulate them in his own work. This admiration led him to question the validity of infinitesimal methods, which he viewed as a departure from the established standards of mathematical rigor. The connection between Rolle's early algebraic work and his later contributions to calculus might appear tenuous at first glance. However, his algebraic background provided him with a unique perspective on the challenges and limitations of calculus. His experience in solving equations and manipulating algebraic expressions equipped him with the tools to analyze and critique the methods employed by Leibniz and Newton. Furthermore, his commitment to rigor and his preference for geometric intuition led him to seek a more solid foundation for calculus, one that could be grounded in the same principles of logical deduction that had guided his algebraic work. This quest for rigor would eventually lead him to formulate the theorem that bears his name, a result that connects the algebraic properties of polynomials with the geometric properties of curves. His initial skepticism, therefore, served as a catalyst for his later contributions, highlighting the importance of critical examination in the advancement of mathematical knowledge. Michel Rolle's initial engagement with the burgeoning field of calculus was marked by a pronounced skepticism, a critical stance rooted in his deep understanding of algebra and his reverence for the geometric rigor of classical antiquity. His algebraic prowess, honed through years of solving complex equations, provided him with a keen eye for inconsistencies and a demand for precise justification qualities that he found lacking in the early formulations of calculus. He perceived a certain looseness in the methods employed, a reliance on infinitesimals that appeared to him as conceptually dubious and insufficiently grounded. The calculus of Leibniz and Newton, while demonstrably powerful in solving problems related to tangents, areas, and volumes, relied heavily on the concept of infinitely small quantities. These infinitesimals, denoted as dx or dy, were treated as quantities smaller than any finite magnitude, yet were manipulated algebraically as if they possessed definite values. Rolle, trained in the algebraic tradition of clear axioms and deductive reasoning, found this approach unsettling. He questioned the logical validity of operating with quantities that seemed to defy precise definition. Rolle's specific criticisms centered on the lack of a clear and consistent geometric interpretation of these infinitesimal operations. He sought a return to the rigorous methods of the ancient Greeks, particularly the techniques of exhaustion employed by Euclid and Archimedes. These methods, while often cumbersome, were based on sound geometric principles and avoided the problematic notion of infinitesimals. For instance, Archimedes' calculation of the area of a circle involved inscribing and circumscribing polygons with an increasing number of sides, ultimately converging on the true area. This approach, based on finite quantities and geometric reasoning, resonated deeply with Rolle's mathematical sensibilities. To illustrate his concerns, consider a typical problem in early calculus finding the tangent line to a curve at a given point. Leibniz's method, for example, involved calculating the ratio of infinitesimal changes in the x and y coordinates represented as dy over dx. This ratio was then taken as the slope of the tangent line. Rolle questioned the validity of this procedure. How could one be certain that this ratio accurately represented the slope of the tangent when both dy and dx were supposedly smaller than any assignable quantity? He felt that the method lacked a clear geometric justification and relied on an intuitive leap that bypassed the need for rigorous proof. Another point of contention was the use of infinite series in calculus. While infinite series provided a powerful tool for approximating functions and solving differential equations, Rolle worried about the convergence and validity of these expansions. He questioned whether one could confidently manipulate infinite sums as if they were finite sums, without carefully considering the potential for error or divergence. He demanded a more thorough investigation of the conditions under which infinite series could be reliably employed. Rolle's skepticism was amplified by the lack of standardization in the notation and terminology of early calculus. Leibniz and Newton, while both developing similar ideas, employed different symbols and approaches, leading to confusion and debate. Rolle sought a more unified and coherent framework for calculus, one that could be grounded in clear definitions and rigorous proofs. He believed that the lack of such a framework hindered the progress of the field and made it susceptible to errors and misinterpretations. His algebraic background further fueled his critical perspective. Algebra, with its emphasis on symbolic manipulation and equation solving, demanded a high degree of precision and logical consistency. Rolle applied these same standards to calculus, scrutinizing every step of the reasoning and demanding clear justifications for each operation. He was particularly wary of arguments that relied on intuition or physical analogy, preferring instead a purely deductive approach based on solid mathematical principles. The influence of ancient Greek geometry on Rolle's thinking cannot be overstated. He saw in the works of Euclid and Archimedes a model of mathematical rigor and clarity that he believed was essential for the development of calculus. He admired their commitment to geometric intuition and their reliance on finite quantities and geometric reasoning. He sought to emulate their approach in his own work, striving to ground calculus in the same solid foundations that had characterized classical geometry. For instance, Euclid's Elements provided a framework for deductive reasoning based on a set of clear axioms and postulates. Rolle believed that calculus should be developed in a similar manner, starting with a set of fundamental definitions and proceeding through a series of rigorous proofs. He questioned the reliance on infinitesimals, arguing that they introduced an element of vagueness and uncertainty that was incompatible with the spirit of Euclidean geometry. Similarly, Archimedes' method of exhaustion offered a way to calculate areas and volumes without resorting to infinitesimals. Rolle saw this method as a more reliable and geometrically sound approach to calculus problems. He admired Archimedes' ingenuity in using finite quantities to approximate areas and volumes, and he sought to adapt these techniques to the challenges of calculus. A concrete example of Rolle's geometric approach can be seen in his critique of finding the area under a curve. While proponents of infinitesimal calculus would divide the area into infinitely thin rectangles and sum their areas, Rolle preferred to approximate the area using a series of trapezoids or other geometric shapes. By carefully analyzing the errors introduced by these approximations, he sought to obtain a rigorous estimate of the true area. This approach, while more laborious than the infinitesimal method, provided a clearer geometric interpretation and avoided the problematic notion of infinitely small quantities. Rolle's deep-seated skepticism towards early calculus stemmed from his commitment to rigor, his preference for geometric intuition, and his algebraic background. He sought to ground calculus in the same solid foundations that had characterized classical geometry, demanding clear definitions, rigorous proofs, and a consistent geometric interpretation of all operations. His criticisms, while sometimes harsh, played a crucial role in stimulating the development of a more rigorous and logically sound foundation for calculus. His concerns highlighted the need for a more careful examination of the concepts of infinitesimals, infinite series, and convergence, ultimately contributing to the formalization of calculus in the centuries that followed. Michel Rolle's name is indelibly linked to a fundamental theorem in calculus, a result that bears his moniker Rolle's theorem. This theorem, in its original formulation, addressed a very specific geometric problem related to polynomial equations and their roots. It provided a rigorous criterion for the existence of a root of the derivative of a polynomial function between two known roots of the original function. Rolle initially conceived of his theorem within the context of his algebraic investigations and his geometric approach to mathematical problems. He was deeply concerned with the reliable identification of roots of polynomial equations. His initial objective was to establish a precise and verifiable method for locating these roots. His theorem offered a way to confirm the presence of a root for the derivative of a polynomial within a given interval, given that the polynomial itself had roots at the endpoints of that interval. The precise statement of Rolle's theorem, as he originally presented it, can be articulated as follows. If a real value polynomial function, f of x, has equal values at two distinct points, and b, then its derivative, f prime of x, must have at least one root between a and b. In simpler terms, if the function starts and ends at the same height, there must be a point in between where the tangent line is horizontal. Rolle's original proof of the theorem was firmly rooted in algebraic manipulation and geometric reasoning. He began by considering a polynomial function, f of x, that has roots at x equals and x equals b. This implies that the function can be written in the form f of x equals the quantity x minus a times the quantity x minus b times some other polynomial q of x. He then proceeded to calculate the derivative of f of x using the product rule. The derivative, f prime of x, is then equal to the quantity x minus a times the derivative of q of x, plus the quantity x minus b times the derivative of q of x, plus q of x times the quantity 2x minus a minus b. Rolle then focused on evaluating this derivative at a point c between a and b. He demonstrated that there existed at least one such point c where the derivative, f prime of c, equaled 0. This conclusion was achieved through a series of algebraic manipulations, exploiting the properties of polynomials and the intermediate value theorem. The core idea was to show that, due to the polynomial's continuity and the difference in signs of f prime of x near a and b, there must be a point where the derivative crossed the x-axis, indicating a root. The limitations of Rolle's original proof stemmed from its reliance on specific assumptions about the nature of the function. His proof was primarily applicable to polynomial functions. He did explore generalizations to other classes of functions. The proof depended heavily on the algebraic structure of polynomials and their derivatives. Furthermore, Rolle's initial formulation lacked the generality and abstraction that would later characterize the modern version of the theorem. It was confined to a specific algebraic context and did exhibit the full power and applicability that it possesses today. To illustrate Rolle's theorem in action, consider the simple polynomial function f of x equals x squared minus 3x plus 2. This polynomial has roots at x equals 1 and x equals 2. Since f of 1 equals 0 and f of 2 equals 0. According to Rolle's theorem, there must be a point between 1 and 2 where the derivative of this function is 0. The derivative of f of x is f prime of x equals 2x minus 3. Setting this derivative equal to 0 and solving for x yields x equals 3/4, which lies precisely between 1 and 2. This demonstrates the theorem's validity in a concrete case. The modern interpretation and generalization of Rolle's theorem within real analysis significantly expands its scope and applicability. The modern formulation states that if a real-valued function, f of x, is continuous on the closed interval from a to b and differentiable on the open interval from a to b, and if f over equals f of b, then there exists at least one point c in the open interval from a to b such that f prime of c equals 0. This modern version eliminates the restriction to polynomial functions, extending the theorem to a much broader class of continuous and differentiable functions. The key difference lies in the focus on continuity and differentiability as the primary conditions. This generalization relies on the completeness of the real number system and the properties of continuous functions on closed intervals. Rolle's theorem serves as a crucial foundation for the mean value theorem, a cornerstone result in differential calculus. The mean value theorem, in essence, is a slanted version of Rolle's theorem. It states that if a function, f of x, is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there exists a point c in the open interval from a to b such that f prime of c equals the quantity f of b minus f of r divided by the quantity b minus a. Geometrically, the mean value theorem asserts that there exists a point on the curve of f of x where the tangent line is parallel to the secant line connecting the points a, f of a, and b, f of b. Rolle's theorem is simply the special case of the mean value theorem where f over equals f of b, making the slope of the secant line 0. Thus, Rolle's theorem provides the essential insight that leads to the more general mean value theorem. Later mathematicians, such as Cauchy, built upon Rolle's initial work to develop more powerful and general results in calculus. Cauchy's contributions to the rigorization of calculus were profound, and he recognized the importance of Rolle's theorem as a stepping stone to more advanced theorems. Cauchy's mean value theorem, a generalization of the mean value theorem, further extended the applicability of these concepts to a wider range of functions. The influence of Joseph Louis Lagrange is also relevant here. Lagrange's work on the calculus of variations and his emphasis on analytical methods provided a framework for understanding and extending Rolle's theorem. Lagrange's approach to calculus, which focused on algebraic manipulation and formal reasoning, resonated with Rolle's own algebraic background and contributed to the development of the modern understanding of the theorem. Rolle's theorem continues to find applications in contemporary fields of mathematics, particularly in real analysis, optimization, and numerical analysis. In real analysis, it is used to prove other fundamental theorems and to establish properties of differentiable functions. In optimization, it is used to find critical points of functions and to determine their maximum and minimum values. In numerical analysis, it is used to develop algorithms for approximating roots of equations and for solving optimization problems. For example, in optimization theory, Rolle's theorem can be used to demonstrate that a local maximum or minimum of a differentiable function must occur at a critical point, where the derivative is 0. This principle is used extensively in various optimization techniques, such as gradient descent and Newton's method, to find optimal solutions to complex problems. Furthermore, Rolle's theorem plays a vital role in proving the uniqueness of solutions to differential equations by demonstrating that the derivative of the difference between two potential solutions must be 0 at some point. One can establish that the two solutions must be identical, ensuring the uniqueness of the solution. In conclusion, Michel Rolle's theorem, while initially conceived within a specific algebraic and geometric context, has evolved into a fundamental principle of calculus with broad applications in various fields of mathematics. Its significance lies not only in its own intrinsic value but also in its role as a cornerstone for more advanced theorems and techniques, solidifying its place as a lasting contribution to the mathematical landscape. Rolle's theorem is a testament to the power of rigorous reasoning and the enduring impact of seemingly simple ideas when placed on a firm foundation. Following his investigations into the nature of algebraic equations and the development of what would become known as Rolle's theorem, Michel Rolle turned his attention toward the practical challenge of solving equations numerically. This pursuit was driven by the fact that many equations, even seemingly simple ones, lack solutions expressible through radicals, necessitating approximation techniques. Rolle's work in this area reflects the influence of earlier mathematicians, particularly François Viet, whose work on algebraic manipulation and equation solving provided a foundation for Rolle's numerical investigations. Viet's innovative methods for transforming equations and isolating roots were crucial precursors to Rolle's own contributions. Rolle's approach to numerical analysis involved a combination of algebraic manipulation and iterative refinement. He sought to develop methods that could systematically narrow down the possible range of solutions, ultimately converging on a numerical approximation of the route. One of the key techniques he employed was the use of transformations to simplify the equation and isolate the roots. These transformations, often involving substitutions or changes of variables, aimed to create a new equation that was easier to solve numerically. For example, consider an equation of the form x cubed minus 3x plus 1 equals 0. This cubic equation, while relatively simple in appearance, possesses roots that cannot be expressed through radicals. Rolle would have approached this equation by first attempting to isolate the roots through algebraic manipulation. He might have explored substitutions such as x equals y plus 1, resulting in a transformed equation in terms of y. This manipulation could potentially simplify the equation and make it easier to identify intervals containing the roots. Once the roots were isolated within specific intervals, Rolle would employ iterative methods to refine the approximation. These methods typically involved evaluating the equation at various points within the interval and using the sign of the result to determine whether the route lay to the left or right of the chosen point. By repeatedly narrowing the interval, he could converge on a numerical approximation of the route to a desired degree of accuracy. Rolle's numerical techniques can be compared to other contemporary approaches, such as Newton's method, which also provided a means of approximating routes through iterative refinement. However, Rolle's methods often relied more heavily on algebraic manipulation and interval isolation, while Newton's method focused on using the derivative of the function to guide the iteration. Each approach had its advantages and disadvantages. Rolle's methods could be more robust in certain cases, particularly when dealing with equations with multiple roots or complex behavior, as they did depend upon derivative calculations, which could be problematic. Newton's method, on the other hand, could converge more quickly when the derivative was well behaved, but was susceptible to issues such as divergence or oscillation. A key advantage of Rolle's techniques was their ability to provide guaranteed bounds in the error of the approximation. By carefully tracking the interval within which the route was known to lie, he could ensure that the approximation was accurate to a certain number of decimal places. This level of rigor was particularly important in a time when numerical computation was often performed by hand and errors could easily accumulate. A disadvantage of Rolle's method was the computational intensity of the algebraic manipulation and iterative refinement. Each step required careful calculation and analysis, making the process time-consuming and laborious. Rolle's work in numerical analysis directly influenced later mathematicians and their work in route finding. His emphasis on algebraic manipulation and interval isolation provided a valuable framework for developing more sophisticated numerical methods. For example, his techniques were built upon by mathematicians who sought to automate the process of route finding through the use of mechanical calculators and early computers. The legacy of Rolle's work can be seen in the development of modern numerical analysis, which relies on a combination of algebraic techniques, iterative methods, and error analysis to solve equations to high degrees of accuracy. His methods contributed to the foundation for algorithms used to solve complex equations arising in fields such as engineering, physics, and economics. Rolle's contributions to numerical analysis also highlight the interplay between theoretical and practical mathematics. While his work on Rolle's theorem was primarily theoretical in nature, his investigations into numerical methods were driven by the practical need to solve equations that arose in real-world applications. This interplay between theory and practice is a recurring theme in the history of mathematics, and Rolle's work serves as a reminder of the importance of both aspects of the discipline. His approach to solving equations numerically involved a process of bounding the roots within successively smaller intervals. This method, grounded in the principles of interval arithmetic, ensured that the solutions were not only approximated but also confined within a range of certainty. For instance, in tackling equations with multiple real roots, Rolle would meticulously determine intervals where these roots resided, employing algebraic transformations to simplify the equation and facilitate the isolation process. This process often involved the strategic substitution of variables to reduce the complexity of the equation, a technique directly influenced by Viètre's algebraic innovations. Consider an equation such as x to the fifth power minus 5x cubed plus 4x minus 1 equals 0. Rolle would initially seek to identify intervals on the real number line where sign changes occurred, indicating the presence of a route. He would then apply algebraic manipulations, such as factoring or substitution, to simplify the equation and refine the intervals containing the roots. For example, he might attempt to factor out common terms or introduce a new variable to reduce the degree of the polynomial. Through this iterative process of interval refinement and algebraic simplification, Rolle could approximate the roots of the equation to a desired level of precision. Compared to alternative methods of his time, such as those relying on infinite series expansions or geometric constructions, Rolle's approach offered a degree of robustness and reliability, particularly for equations where other methods might falter due to convergence issues or computational complexity, while Newton's method, known for its rapid convergence, could sometimes lead to unstable results or require careful selection of initial guesses. Rolle's method provided a more conservative approach, guaranteeing convergence within the identified intervals. The influence of Rolle's numerical methods extends to the development of modern algorithms for route finding. While his specific techniques may not be directly implemented in contemporary software, the underlying principles of interval arithmetic and iterative refinement remain fundamental to many numerical algorithms. For instance, dissection methods, which repeatedly bisect an interval containing a route, owe their conceptual foundation to Rolle's emphasis on interval bounding. Similarly, methods that combine algebraic transformations with numerical iterations, such as those used in computer algebra systems, reflect the spirit of Rolle's approach to equation solving. His work laid a foundation for subsequent advancements in numerical analysis, influencing mathematicians who sought to develop more efficient and accurate methods for approximating roots of equations. The legacy of Rolle's work is evident in the continued emphasis on interval arithmetic, iterative refinement, and error analysis in modern numerical algorithms. Michel Rolle's career ascended to new heights with his appointment to the Académie Royale des Sciences. This prestigious institution, a hub of intellectual exchange and scientific advancement, provided Rolle with a platform to engage with the leading minds of his era. His duties within the Academy involved evaluating scientific submissions, participating in scholarly debates, and contributing to the collective pursuit of knowledge. The Academy served as a crucible where his mathematical ideas were tested, refined, and disseminated. The environment within the Academy profoundly shaped Rolle's mathematical development. He benefited from the rigorous scrutiny of his peers, who challenged his assumptions and pushed him to defend his arguments with greater precision. These interactions forced him to articulate his ideas more clearly and to address potential weaknesses in his reasoning. The constant exposure to new mathematical concepts and techniques broadened his intellectual horizons and stimulated his own research. Rolle's influence on the mathematical discourse of the period stemmed from his active participation in the Academy's activities. He presented his own findings, critiqued the work of others, and engaged in lively debates on topics ranging from algebra to calculus. His contributions helped to shape the direction of mathematical research and to establish standards of rigor and clarity. He became a respected voice within the mathematical community, whose opinions carry considerable weight. His relationships with other prominent mathematicians, including figures associated with Leibniz and Newton, were complex and multifaceted. While direct collaboration may have been limited, his correspondence and intellectual exchanges with these individuals reveal a dynamic interplay of ideas. For instance, while details of direct correspondence remain scarce, the intellectual climate fostered by Newton's and Leibniz's groundbreaking work undoubtedly permeated the Academy, influencing the debates and discussions in which Rolle participated. He engaged with their followers, scrutinizing their applications of calculus and challenging their interpretations of its fundamental principles. These interactions, even when adversarial, spurred further investigation and refinement of both algebraic and calculus-based methods. The overall significance of Rolle's work lies in its contribution to the development of both calculus and algebra. His early work on algebraic equations provided valuable tools for solving practical problems and laid the groundwork for later advancements in numerical analysis. His theorem, which bears his name, became a cornerstone of calculus, providing a fundamental link between the values of a function and its derivative. His initial skepticism toward calculus, stemming from concerns about its logical foundations, ultimately led him to a deeper understanding of its power and utility. The evolution of his views on calculus is particularly noteworthy. Initially, he voiced reservations about the rigor of infinitesimal methods, echoing concerns shared by other mathematicians of his time. He sought to ground calculus in more solid algebraic foundations, emphasizing the importance of precise definitions and logical deductions. Over time, however, he came to appreciate the effectiveness of calculus in solving a wide range of problems. His eventual acceptance of Rolle's theorem, a result firmly rooted in the principles of calculus, marked a significant turning point in his intellectual journey. The historical trajectory of Rolle's theorem itself is instructive. It represents a key step in establishing the relationship between the derivative of a function and its values. Specifically, the theorem states that if a continuous function on a closed interval has equal values at the endpoints, then there exists at least one point within the interval where the derivative of the function is zero. This seemingly simple result has profound implications for understanding the behavior of functions and for solving optimization problems. The theorem's genesis can be traced to Rolle's attempts to understand the behavior of polynomial equations. He observed that between any two roots of a polynomial, there must exist a point where the derivative of the polynomial is zero. This observation initially confined to polynomials, was later generalized to a broader class of functions, becoming the Rolle's theorem known today. The immediate impact of Rolle's theorem was to provide a rigorous justification for certain techniques used in calculus. It allowed mathematicians to prove the existence of critical points, which are points where the derivative of a function is zero or undefined. These critical points are essential for finding the maximum and minimum values of a function, which has numerous applications in optimization problems. Later, the theorem served as a foundation for more advanced results in calculus, such as the mean value theorem. The mean value theorem generalizes Rolle's theorem by stating that there exists a point where the derivative of a function is equal to the average rate of change of the function over an interval. Rolle's theorem can be seen as a special case of the mean value theorem, where the average rate of change is zero. The reception of Rolle's theorem was initially mixed. Some mathematicians questioned its significance, viewing it as a relatively minor result. Others recognized its importance as a fundamental principle of calculus. Over time, the theorem gained wider acceptance and became a standard tool in the calculus toolkit. Rolle's work was directly influenced by the algebraic traditions of his time. He drew inspiration from the work of earlier mathematicians who had developed methods for solving polynomial equations. He sought to extend these methods and to apply them to a broader class of problems. His initial skepticism toward calculus also reflected the influence of algebraic thinking, which emphasized the importance of precise definitions and logical deductions. Rolle's work directly influenced later mathematicians who sought to develop more rigorous foundations for calculus. His emphasis on precise definitions and logical deductions contributed to the development of analysis, a branch of mathematics that deals with the theoretical foundations of calculus. His theorem, which bears his name, became a cornerstone of analysis, providing a fundamental link between the values of a function and its derivative. In conclusion, Michel Rolle's contributions to mathematics, particularly his work on algebraic equations and his theorem in calculus, cemented his place in the history of the discipline. His membership in the Académie Royale des Sciences provided him with a platform to engage with the leading mathematical minds of his era, shaping his intellectual development and influencing the mathematical discourse of the time. His initial skepticism toward calculus, coupled with his commitment to algebraic rigor, led to a deeper understanding of its power and utility. His legacy endures for Rolle's theorem, a fundamental principle of calculus that continues to be taught and applied in mathematics and related fields. While his name may be less widely recognized than those of Newton or Leibniz, his contributions represent a significant chapter in the evolution of mathematical thought, revealing the complex interplay of algebra and calculus in the development of modern mathematics. His work serves as a reminder that progress in mathematics often arises from a combination of skepticism, rigor, and a willingness to challenge established ideas.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.